Jai to all. I am Samender Singh, Assistant Professor in CSC Department. My college name is Akgec Engineering College, Ghaziabad. My topic is convex optimization in Unit 1 of the code KDS 071. Course outlines a definition of convex optimization, key elements of convex optimization. Then we will cover some normal examples of convex optimization. After that, the most important topic of this first unit, that is linear programming, in which we will cover some numerical convex optimization. As this, you can see this is made up of two words. First is convex, the second is optimization. Optimization is a very general terms having optimal value, where according to our application, if we need to a relative problem, if we want to maximize, or according to problem in a minimum also. So as a definition, we have convex optimizer refers to the field of mathematical optimization that deals with the problems where both the objective functions and the feasible regions, where feasible regions is also known as constraints, are convex. Convexity in this context refers to a mathematical property where a function defines over a convex set satisfies certain condition. Before comes to this topics, here I am using a term convex that clearly means a region of each point of it will be a convex. Suppose if we have this particular region, this will be convex if each point of this one, every point that lie between boundaries of this region, if we connect any 2 points, on connecting these 2 points, the line segment, if this line segment completely inside this region, then this is known as convex. And if any part of this line comes outside this figure, then this will become concave, or we can say non-convex. Suppose just like this one. Suppose these are two top, and when we connect these 2 points, we are getting a line segment. This portion is not inside the given figure, so this is not convex. This is non-convex. Now you are clear what is convex. So when we apply this concept in convex optimization, then context refers to a mathematical property where a function contain each value must also satisfy by this convex property. Now these are some elements of convex optimization. First is convex function. As I told earlier, a function is considered convex if the line segment between any 2 points on the graph of the function lie above or on the graph itself. In simple terms, a function is convex if its shape like a bowl, meaning there are no local minima, any points on the line joining 2 points on the convex lie above the function itself. I already defined this thing. Then second key element is convex set. A set is convex if for any 2 points in the set, the line segment joining those points lies entirely within the set, just like this one. Suppose this is convex function, then each point inside this region, when we connect these two, as this line segment lie inside this function. This is convex function, and convex set will contain all the points just like this one, P1, P2. So P1, P2, and all points lie inside this function is also forming a set which is known to be convex set. Now the next terminology that is opposite to first, that is convex set, that is it is non-convex set. So example of non-convex set is a non-convex set such as a crescent moon shape or horseshoe. So basically what we need to see in this one, we need to find 2 points x and y inside the set with the line segment connecting them intersecting the boundary of the set. So when we connect these points, some line segment portion will be outside the set. So it is known to be non-convex set. Now convex set exhibit a bulging outward property where any line segment connecting 2 points inside the set remains entirely within the set. Non-convex set can have indentations or hole causing line segment between points to intersect with the set's boundary, violating the convexity property. So we can say anything which violating the convexity property will be considered as non-convex set. Now we have examples. Convex optimization problem seeks to minimize or maximize, both known to be optimal, a convex objective function over a convex set of feasible solutions. These problems have many applications in various fields such as engineering, very common, economics, machine learning, statistics, and many more. So generally in our subjects we are using machine learning as an example of this convex optimization. They are particularly advantageous because they often have globally optimal solution and efficient algorithm for finding these solutions. There are various algorithms and methods to solve convex optimization problem such as gradient descent. We will cover this topic in unit 3. Then interior point methods and the method of Lagrange multiplier. These are very common examples in machine learning used in convex optimization. These methods take advantage of the spatial structure of convex problem to efficiently find the optimal solution. The significance of convex optimization lies in its applicability to a wide range of real-world problems where the objectives and the constraint exhibit convex behavior, making it possible to find optimal solution reliably and efficiently. Now, as an example, first, linear programming. Linear programming involves optimizing a linear objective functions subject to linear inequality and equality. So both comes inequality and equality. Constant linear programming problems are prevalent in resource allocations, production planning, transportation, and network flow optimization. These are the area where we use linear programming. For instance, optimizing production label given limited resources or minimizing costs while meeting production demands are classic application of linear programming. So this is very broad topic in machine learning. Next is quadratic programming. It deals with optimizing a quadratic objective function subject to linear constraint. Quadratic programming problems are widespread in finance for portfolio optimization, where the goal is to maximize return while managing risk within specified constraint. They are also used in control system and support vector machine in machine learning. Next, third is least square problem. So least square problem or optimization problem involves minimizing the sum of squares of the differences between observed and predicted values. It is widely used in regression analysis. It is widely used fitting curves to data, signal processing, and machine learning algorithms like linear regression. Next, in conic optimization involves optimizing a linear objective functions over the intersection of convex set defined by convex cone. Semi-finite programming is a subset of conic optimization and is applied in various fields such as engineering, system control, combinatorial optimization, and quantum mechanics. So these are 4 fields of convex optimization. Now we will first cover linear programming. What is linear programming? It is a mathematical technique used to optimize a linear objective function subject to a set of linear equality and inequality constraints. So let's take a simple example to demonstrate what is linear programming. As a numerical, we have a given problem. We need to maximize the objective function. This is the objective function, a linear equation, that is z equal to 5x plus 3y. So it is our objective function that we have to maximize. Now we have certain constant. We have given 4 equations. First is 4 inequalities that are constant. So 2x plus y less than or equal to 20, first constant, then 4x minus 5x greater than or equal to minus 10, and then we have 2 other constant, that is x greater than or equal to 0 and y greater than or equal to 0. So we have basically 4 constant. These 4 constant on an objective function that we need to maximize. So what are the steps to solve linear programming? As a first step, we need to identify the decision variables and then write the objective function and constraint in terms of these variables. So in the given problem, we have 2 variables or decision variable, x and y. So x is the number of units of products x produce and y is the number of units of product y produce, and we have given this is our objective function. It is a simple linear equation, and then we need to write the constant in terms of these variables. So we have already given these constant as a 4 equations in terms of these decision variables. Then we have second step. What is second step? Then we need to graph the constant to identify the feasible region. In this problem, we have 4 constant, so we need to plot the graph of these constant. And then we have feasible region. And let's plot the constant on the graph. First inequality, or we can say first constant, that is 2x plus y less than or equal to 0, 20. So we have 2 values. First is 10 or 0. This is our first point. And then we have second point, that is x0, y0, 0 and 20. So these are 2 points. By connecting these 2 points, we are getting one line. Suppose this is our graph. this is 0, then 5, this is we can say 10, 20. In the same manner, we have 10, 20. So first point, what is? This is first point, and second is 0, 20. This is 6. So on connecting these ones, so this is our first constant, or we can say this is our first line. This is first constant. This is our first constant. Then this constant represent a line in the xy plane. We can plot this line. So in the same manner, we need to find second constant line. So what is second constant? This is our second constant. In the same manner, we need to find the line representing this one. And in the same way, we need to find line of this and line of this. You can see these line denoting these two will be the first quadrant, or we can say positive quadrant of the xy plane. So this is our third one, and this is fourth one. So these two lines represent the third and fourth constant. In the same, we have second constant, that is 4x minus 5y greater than or equal to 10. So we have 2 points, that is 0, 2 and 5, 2. Again 2 points, suppose let's take these two. So first is 0, 2, it will be around there, and second is 5, 2. 5, 2 is there. So on connecting these two, this will be like this one. So we are getting first constant, this is our second constant, this is our third constant, this is our fourth constant. So we are getting 4 constant graph. On connecting, plotting these 4 constant on the xy plane, we are getting like these. Now, what is the next step? Third step. Identify the corner point of the feasible region. How we can get the feasible region? The corner points are the intersections of the line representing the constant. So connecting, this is first line, or we can say this is first intersection point, then this is second intersection point, then this is third intersection point. So this is the feasible region. Feasible region. In the third step, we need to find this feasible region by connecting intersection point of these constants. So this is first, then this is second, then this is third. Now we are getting this feasible region related to our problem. Identify the corner points. We are getting corner points by collecting all intersection points of the feasible region. The corner points are the intersection point of the line representing the. Now in the next, evaluate the objective function at each corner points, that is z equal to 5x plus 3y. As this is our objective function, by collecting all corner points, we are getting the maximum or minimum result. In this particular problem, we need to find the maximum result. So we will apply all these corner points to this objective function, and we are getting the maximum value. This is how we can get the maximum or optimized value by objective function. And then determine the maximum or minimum value. On apply these corner points to our objective function, we are getting final result, or we can say maximum or minimum values of the objective function. Now we have a practical problem. Now we will discuss some practical problem, and then we will see how this approach is applied to our practical problem. Very common problem is transportation problem. We will apply linear programming on it. Let's read out what is our problem. A company has 3 factories and 4 warehouses. the cost of shipping one unit of products from each factory to each warehouse is given. The company needs to determine how many units of is shipped from each factory to each warehouse to minimize total shipping cost while satisfying demands at each warehouse and supply at each factory. So this is our practical example. Now we need to find linear, minimum result. So this problem having needs to find the minimum cost. So as you can see, this is we need minimum total as a optimization. So let's formulate this given problem. So first we need to find the decision variables. As you can see here, 3 factories and 4 warehouses. So all these are the decision variables of our problems. These are 3 factories, F1, F2, F3. Then we have 4 warehouses, W1, W2, W3, W4. So these are our decision variables. Now next term is cost of shipping one unit of product from each factory to each warehouse. Let's formulate this one. X I to J. What is mean of I to J? It is number of unit to be shipped from factory I to warehouse J. First thing. Then we have Cij. This is cost. What is cost? Cost of shipping one unit from factory I to warehouse J. So as a X, it will represent the number of units to be shipped from factory I to warehouse. These are the number of units. X representing number of units. And C representing cost, related cost. And in the same way, we have 2 other find. J, demand of warehouse J, S, supply at factory I. So these are our 4 other terms that we need to find. Then solution. As a solution, we need to minimize the total shipping cost, which is the sum of cost of shipping from each factory to each warehouse. So this is our entire solution. That is minimum of Z will be equal to summation of I equal 1 to 3 and summation J to 1 to 4, Cij and Xij. These are the cost related to each product. Then subject to following constant. What we already told you that we have certain constant. It is also discussed. So first constant is supply constant. The total unit shipped from each factory cannot exceed its supply capacity. This is our first constant. Then we have demand constant, that is total unit received at each warehouse must meet its demand. This is our second constant. And in the third constant, we have non-negativity constant, that is total number of units shipped cannot be negative. So these are our 3 constants. So this is how we formulate our problem. So in this video, I am discussing one practical example on which I apply linear programming. So in same way, we have number of practical problems that can be solved by linear programming.